All right, today we're going to talk about collision theory and some ways to affect the rate of a reaction. So what you can see on the right-hand side is an energy distribution of molecules with different energies. We saw this when we were doing temperature of gases and how when you heat up a gas, the distribution shifts to the right. So something important to note here that we're going to talk about is activation energy, which is the energy needed for the reaction to happen. And so shaded in red over here are the molecules that have an energy greater than or equal to the activation energy. And so those are the particles that have enough energy to react. They still need to react in the correct orientation for the reaction to happen. They still need to collide in the correct orientation for the reaction to happen. So some stuff we already talked about. Increasing temperature is going to shift your graph from slower speeds to higher speeds. And this is going to do two things. It's going to increase the frequency of collisions because the molecules are moving faster. And it's going to increase the proportion of effective collisions, which are the molecules that have a higher energy. And it turns out that the second is actually the effect that is the most important. So while there are more collisions, what is more impactful is that the proportion of effective collisions goes up. And you can see that as the distribution shifts to the right, not only it also gets broader, which means that this increase in area is really significant. Okay, so something else you want to know is that the orientation needs to be a certain way for a reaction to happen. So here are a couple ways that a nitrogen monoxide and an ozone molecule can collide to create, ideally, nitrogen dioxide and oxygen. So the reaction that's trying to happen is NO plus O3 goes to NO2 plus O2. Something we haven't really thought about is how does this reaction happen though? And so we know that the molecules have to collide, but they have to collide in a specific way. So if we look closer at this, what we are trying to do is make a nitrogen-oxygen bond. And we need to break an oxygen-oxygen bond. And so for those two things to happen, they need to collide in a specific way. And ideally, one of the nitrogens and one of the oxygens from ozone are going to collide. And that is going to allow the nitrogen-oxygen bond to be formed. And so you can see up here in the ineffective collisions, if the oxygen side collides with another oxygen, you cannot make a nitrogen-oxygen bond. And then if the nitrogen collides with the middle oxygen, the two remaining oxygen atoms wouldn't be attached to each other anymore. So that also is ineffective. So this kind of theory requires you to think about what bonds need to be made, what bonds need to be broken, and where the atoms should collide for that to happen. Okay. Sorry, I'm always worried that it's going to stop recording. Okay. So we're going to be drawing a lot of these energy diagram, reaction coordinate diagrams. This shows the reaction progression from the reactants to the products. This is something you might have seen a little bit in Chem 1, but they're really important in understanding what's happening. We'll talk about delta G towards the end of the year. This is Gibbs energy, which has to do with if the reaction is going to happen spontaneously or not. But for now, you can just think about this as the energy of the reaction. And if you were to draw a line from the reactants to the products, this distance here is the enthalpy. And if the reaction is going downhill, it's exothermic. And if it goes uphill, it's endothermic. And that's because exothermic reactions are releasing heat, and we see that by the products being lower in energy than the reactants, because the reactants have released heat, they have released energy, they have lost energy. Okay, so what is new is this idea of going from the reactants and giving the reactants enough energy to react. And so the difference between the reactants and the top of this hill is considered the activation energy. And at the top of the hill, the orientation of the molecules is called the transition state. And if you understand the transition state and you can lower the energy of the transition state, you would end up lowering the activation energy. And while that might seem like a simple idea, the scientist who, forget their name, actually won a Nobel Prize for this kind of theory and proposing this. So it's a pretty big deal. It's really important in organic chemistry when you start to think about different reactions and trying to understand why they happen. So in this example that's being shown, we are starting with methyl bromide, and we're taking a hydroxide anion, and the hydroxide anion and the bromide are swapping spots. This is called an SN2 reaction, which is something, again, you'll learn a ton about in organic chemistry. But the transition state is the hydroxide kind of forming the bond with the methyl group and then the bromide leaving. Okay, so activation energy, minimum amount of energy required to initiate the reaction. Transition state, also sometimes called the activated complex, because it has been activated by applying the activation energy, is very, very, very unstable. It is the top of the hill. It's very fleeting, so it doesn't last for a very long time. And it represents the peak of the energy barrier. And once you get to the activation energy, the transition state, which is sometimes denoted with this symbol, that set of atoms could go either direction. So it's downhill, it's exothermic in both directions. And so there's nothing to stop the reactants from going downhill back and falling apart. But especially if this is an exothermic reaction, what can happen is once the reactants go this way and they fall into the products, the hill that they would have to reach to go backwards is too big. And so they stay as the products. All right, so one of the things that catalysts do is they lower the activation energy. This is how they increase the rate of the reaction. And so this could be represented with an energy diagram. If this is your normal activation energy, adding a catalyst is going to reduce that activation energy so that way more of the molecules can react. If you were to draw this as an energy diagram, you would lower the peak of your hill so that the activation energy with the enzyme is less than the activation energy without the enzyme. Something that we also know is that temperature increases reaction rate. It also does this by changing the rate constant K. So K depends on temperature. It also depends on activation energy. It is a nonlinear change, so a good rule of thumb is that for every 10 degrees Celsius increase in temperature, reaction rates tend to double. Okay, so there's a equation that relates K to temperature and activation energy. It is called the Arrhenius equation. And the equation is K is equal to AE to the negative EA over RT. And this is E to the negative EA over both R and T. So those are both in the denominator of the fraction. Okay, and what K is describing is the number of collisions which will result in a reaction. A is the total number of collisions. So not necessarily the ones with enough energy, but just every single time that the atoms collide. This is also considered the frequency factor. It is a constant that you can look up. And we assume that A doesn't change within the temperature range that we are looking at, although oftentimes that's not a great assumption. But we don't really focus as much on A, we really focus on EA and T. And you'll see why in a minute when we kind of rearrange this equation. So E then to the negative EA over RT is the probability that any collision will be effective. So if you take the total number of collisions and you multiply it by the probability that a collision will be effective, you end up with the number of collisions that are effective. Okay. And what we can see is that if you increase activation energy or if you decrease temperature, you are going to increase the value of K. Okay. So again, something we want to do is be able to plot this as a linear graph. So we need to rearrange K, AE to the negative EA over RT into a y equals mx plus b form. So what we can do is we can take the natural log of both sides, and we get ln K equals ln AE to the negative EA over RT. Exponent comes out in front, we get ln K equals negative EA RT plus ln A. Okay, and this now looks like a linear equation. Ln K is going to be our y variable. Negative EA is going to be our slope. 1 over t is going to be our x variable, which actually, let's rewrite this to make it a little bit more explicit. Negative EA over R times 1 over t plus ln A. Okay, so now we can see negative EA over R is going to be M, 1 over t is going to be x, and then ln A is going to be our plus b. So if we plot ln K versus 1 over t, we're going to get a straight line. Our slope will be negative EA over R, and our y-intercept will be ln of A. EA is going to be in joules or kilojoules. R is going to be 8.314 joules per mole Kelvin. Temperature needs to be in Kelvin. And then you need to make sure that your activation energy and your R match in units. Oftentimes activation energies are really big numbers, so they're usually going to be reported in kilojoules. So you either need to change your activation energy to joules or change your R value to kilojoules. All right. What is also useful is being able to determine the activation energy given a K at 2 different temperatures. And I have the math here. This is one of the ways you can combine the 2 equations. So what we can do is we can write out this equation for a slope 2 times. So ln K1 equals negative EA over RT1 plus ln A. Ln K2 equals negative EA over RT2 plus ln A. We are assuming A doesn't change. And also that the activation energy is a constant, so we're not adding a catalyst or anything. What we can then do is subtract both sides of this equation from this equation. So on the left-hand side, we're going to have ln K1 minus ln K2. And then on the right-hand side, we're going to have negative EA over RT1 plus ln A minus negative EA over RT2 plus ln A. So these 2 go here. And then these 2 go here. Okay, so then we can simplify this. Log A minus log B is log A over A. We can bring out EA over R, because that's a constant. The ln A's cancel out. And then what we're left with before we rearrange that on the inside would be negative 1 over T1 minus negative becomes a positive plus 1 over T2. And then we can rewrite that as 1 over T2 minus 1 over T1. You will also see this written with the negative sign factored out. So these are the same equation, just written in 2 different ways. What's important is that whichever equation you decide to use, you match up your two sets of variables. This is very easy to get confused, so it's a good idea to check at the end and make sure your answer makes sense, which is something I'll show you in a practice problem. Okay. So here we have some information, temperature and rate constants. We can see that as the temperature increases, rate constant also increases, and we want to calculate the activation energy and rate constant at 430 K. Okay, so first thing you could do is graph this. And because we have a bunch of data points, graphing is usually the better of the 2 answers because it's going to include all of the data points. So if you graph ln K versus 1 over T, which you can pause the video, pull up Desmos, and try this on your own, or you can take my word that I hopefully did this correctly. Your slope is going to be negative EA over R. Here is the slope that I got from my equation, so negative 19038 is equal to negative EA over 8.314 joules per mole Kelvin. 1,038, you multiply 8.314, you divide by 1,000. I'm hoping you get 158 kilojoules as your answer. You might be wondering, where does the Kelvin go? The Kelvin gets canceled out with the fact that we're plotting 1 over T. Okay, so then from there you could use the equation You could, sorry, I guess I forgot to say I changed my temperatures into Kelvin. So then what you can do is you can plug in 430 Kelvin into the equation and then solve for K, which you should try to do on your own and then check to make sure that you got the same thing as me. Okay, the other way you could do this is to use the equation that has two K's, two T's down here. Again, pause the video, see if you can plug in the values, get the same answer as me, given the fact that K is 2.52 times 10 to the negative 5, and EA is 158,281 joules per mole. And this is all at 189.7 degrees Celsius. What I did was I called this K2, I called this T2, 189.7 plus 273 gives us 462.7 Kelvin. I plug that in for T2. And then we're solving for what is K1 at 430. You could have totally swapped all of your numbers. There's nothing requiring you to say that the given data points are T2 and K2. Honestly, you probably called them K1 and T1. As long as you do your math correctly, you should get the same answer. And your units of K are the same as whatever units you started with. And this is pretty close to what we got from our graph in the previous problem. It's slightly different, but it's like same order of magnitude, pretty close. Okay, and when I said check to make sure that this makes sense, what I know is that 430 Kelvin is a lower temperature than the temperature that we were given information about. So I would expect my rate constant that is associated with 430 Kelvin to be smaller than my rate constant that is associated with 462 Kelvin. So that makes sense. If you didn't get that as your answer, I would think you dropped a negative sign somewhere or you mixed up where T2 and T1 go.